Let's see exercise 4 next. In this one, we have the usual metric space of real numbers. So that means this D is the standard metric. We have to give an example of a continuous function f from R into R and an open subset V of R such that the image of V under f is not open. As an example, we can take this very simple function, the constant function 0, which we know is continuous. Now note that R as a subset of itself is open, but the f image of R is the singleton set 0, which is not open. Next, exercise 5, that is also similar. In this case also it's almost the same thing, but now you have to produce a continuous function and a closed set f this time, not open, such that the f image of f is not closed. This time let's consider this function. F of x is 2 to the power minus x. If you go back and see the statement of proposition 9.4.10, where we discussed exponentiation and continuity of such functions, such exponential functions, you will see that this is a continuous function. Now you consider this sequence f of n, where say n varies over all the natural numbers. The limit of this sequence is easily seen to be 0, and that is why 0 is an adherent point of f of R. That means it belongs to the closure of f of R. Note carefully that this is a sequence in f of R because natural numbers are after all real numbers. But 0 is not an element of f of R because for 0 to belong to this image, 0 has to be equal to 2 to the power minus x for some real number x, which is not possible by one of the properties of exponents. So that is why, although this point belongs to the closure, but it's not in the set itself. So that means the closure is not equal to the set, and that's why this image is not closed, in spite of having R a closed subset in itself. So this is your example. Next, we have exercise 6, where we are being asked to prove corollary 12.5.9. So this was the statement, let x comma d be a metric space in which we have a sequence kn of non-empty compact subsets such that things go like this: k1 contains k2, k2 contains k3, and so on. It's a nested sequence. We have to prove that then the intersection of all these kn's is non-empty. We start the solution by considering these differences k1 minus kn for all positive integers n, and we are calling the nth difference Vn. By corollary 12.5.6, each kn is closed in k1. Why? Because compact subsets in a metric space are closed, and each kn, because of this containment, is a subset of k1, so a subspace of k1 as well. So that's why we have this. So each Vn is open in k1, complements of closed sets are open. Now our aim is to prove this, but say it's not true. That is, we are supposing that the intersection is empty. Then we have this. You start with k1. In place of k1, you can write k1 difference the empty set. And then in place of this, you write this intersection. And then by one of the two De Morgan's laws, the general version, this equals the union of k1 difference kn as n goes from 1 to infinity. That is, it's the union of the Vn's as n goes from 1 to infinity. Okay, now k1 is a union of these Vn's which are open in k1, and k1 is compact. So by theorem 12.5.8, the one that we proved recently in another analysis video, k1 will be contained in finitely many of such Vn's, their union. So there will exist positive integers n1, n2 and so on, so up to nk, such that k1 is contained in the union of these V's, Vn1, Vn2 up to Vnk. Now among these finitely many positive integers, there is a maximum. Say that maximum is n. Then this union will be equal to Vn, V that maximum suffix. But exactly how? This is how this sequence is given to us, right? I mean, these containments are given to us. The further down the sequence Kn we go, the smaller the sets get. But then when you are taking complements of those sets in K1, the entire direction gets reversed. K1 difference K1 now is the smallest. It is contained in K1 difference K2, which is contained in K1 difference K3 and so on. But we named these sets respectively V1, V2, V3 and so on. So you now get this other chain of containments. And from this it is clear that if say you have finitely many such Vn's, then that V with the largest suffix will be the largest one, which will contain the other V's inside of it, and that's why the union will be the V with the largest n. That is why. But then K1, which is originally contained in this union, is now contained in Vn, and Vn by definition is K1 difference Kn. So K1 is contained in K1 difference Kn. That forces Kn to be empty, which is a contradiction because the original hypothesis says that the Kns are non-empty compact sets. So that is why our supposition must be wrong. So this intersection cannot be empty. So this is where the solution ends.